Today we're going to talk about balancing redox reactions, and specifically in acidic solution. There are a variety of rules that you can use to go by in order to balance these reactions, and I'll be referring back and forth to these, but in all honesty, I don't really just like sit and go through them and read through them because you can do that on your own. What we're going to do is just start using these rules to balance some of these redox reactions, and I'll discuss the rules as we go. So let's look down here at some examples. The first thing we want to do is to do some of the things that we've already been working on, writing these as net ionic reactions, finding out the substance oxidized, substance reduced, getting our half reactions. That's always the first step. So let's start in with that process. So first of all, aluminum nitrate is going to ionize. The nitrates will drop out. We'll be left with Al3 plus Fe yields Fe2 plus Al. The next step then is to get this, again, the substance oxidized and the substance reduced. Since both iron and aluminum are free here, they have 0 for an oxidation number. So iron is going to increase and in oxidation number, which means it's the substance oxidized. Aluminum is going from +3 to 0. It's the substance that's reduced. And that's how we're going to write our half reactions. We've got iron forming Fe2 plus. And remember, we add electrons to one side of these reactions in order to balance out the charges. Since this is the oxidation reaction, we are going to need to put 2 electrons being given off on the right-hand side of the reaction. Those 2 electrons will, along with the +2 charge from the iron ion, will end up giving us a 0 overall charge on that side to match the 0 from the Fe on the left-hand side. So now the next one, the reduction reaction, is going to be Al3 plus reacting to form Al, 0 with no charge. And that's going to give us a 3 electron change. Reduction is gain of electrons. So those are our half reactions. Since these are already balanced by mass, there are no extra atoms to worry about balancing, no oxygens or hydrogens or anything. All we need to do is simply make sure that our electrons are equal. We have to have the same number of electrons lost as the electrons are gained. So if you look, we have 2 electrons being given off in the oxidation reaction and 3 electrons being gained. In order to get those electrons equal, it looks like we're going to need to multiply this top reaction by 3 and this bottom reaction by 2. So let's show what happens when we do that. We end up with 6 electrons, 3 iron ions, and 3 metallic iron atoms once we multiply by that 3. And I always mark it out so that I don't try to do anything stupid and try to multiply anything again. For aluminum, we end up with 2 aluminum atoms, the 6 electrons being gained once again, and 2 for our aluminum ions. This must always result in the electrons being canceled. 6 electrons given off, 6 electrons gained. Those are going to have to equal out. And we're going to simply write whatever's left for our overall reaction. Looks like we've got 3 Fe's plus 2 Al3 pluses. And that's going to yield 3 Fe2 pluses and 2 Als. Now our last step is always to make sure that our overall charge is balanced. And if you'll look right here, we have 2 aluminum 3 pluses. That's going to give us 6 positive charges on the left, and 3 iron 2 pluses, which is going to end up with a 6 electron or 6 positive charges on the right. So this is balanced by both mass and charge now, and that's going to be our overall balanced equation. Okay, so let's look at the next one. And I'm going to erase off some of this that we've done right here so that it won't get too busy up here on the screen and make it more difficult to see what's going on. Both cobalt and bromine over here are elements, so they're not going to ionize. But cobalt bromide is ionic, and if you look it up, it does ionize. So we're going to show that as being split, if you will. So when we write this as a net ionic, it's going to be cobalt plus Br2 yielding CO3 plus. Now remember, and this is the most missed thing, guys, you have to remember you do not carry down those subscripts unless they're part of a polyatomic ion or a diatomic element. So that's what we should end up with at this point. So now we can look at charges. Since the cobalt and the bromide over on the right already have charges, and both of these are elements, so they're both 0 for oxidation number, looks like that was pretty easy. So let's look at what's being oxidized and what's being reduced. We've got cobalt going from 0 to +3. So that's our oxidized substance. We've got bromine going from 0 to a negative. So there's our reduction reaction. So let's write those half reactions down. For our oxidation, we've got cobalt again going to CO3 plus. Remember, oxidation is loss of electrons, and it looks like we need a loss of 3 electrons here in order to show that. And so we've got our 0 on the right-hand side overall for charge and 0 on the left-hand side for our free cobalt. And now let's do the same thing with bromine. Br2 reacts to form Br minus. Now remember, it's balanced by mass first and then by charge. So please don't forget that since I have 2 bromines on the left, I also need 2 bromines on the right. Since this is an overall, since it's 0 for bromine, I'm doing this in green because I really don't want to see this part in your final answer. But think about it, even though we've got 2 bromines here, they're both 0, so we've got an overall 0 charge here, or oxidation value here. Over here we've got 2 -1 charges. So we end up here with a -2 overall charge. So it looks like we've got a 2 electron change. So we need to show that. Remember, I don't want to see the green in the final reaction. So once we do that, now we need to make sure that our electrons match. And since we have 3 electrons, looks like I left off the electron in that one. Since I have 3 electrons in the first reaction, oxidation, and 2 electrons for reduction, I need to multiply this top reaction by 2 and this bottom reaction by 3 to get those electrons to match. So I've got 6 electrons and 2 for each of the cobalts. That took care of that too. I've got 3 for the bromine, 6 for the electrons, 6 for this bromine when it's multiplied by 3, and that takes care of this. So now the electrons cancel, and overall I'm left with 2 cobalts plus 3 bromine diatomic molecules, if you will, and that's going to yield 2, almost made that a capital O, that would be bad, 2 cobalt 3 pluses plus 6 Br minuses. So if we look at our overall charges, you'll notice that over on the left-hand side, both of these are 0 for an oxidation number. I've got +6 for the cobalt and -6 for the bromine. Looks like my charges have balanced out to 0 on both sides. So there's my reaction, balanced reaction for this particular redox reaction.